famous cavity. So it's just something like metallic vibrating here, and it affects the capacitance of this LC resonator. So this can be seen now as LC resonator with movable capacitance. So this is a parametric coupling, which distinguishes it from this linear coupling with qubits. And the coupling, so this B's are the mechanical oscillator and A is the cavity. And the coupling is that this mechanical position changes the cavity frequency. And this G0 is called the radiation pressure coupling. And it can be connected to how much the cavity capacitance depends on the mechanical position. And the cavity parameters are something very typical for the qubits. Mechanical frequencies are often in the range of tens of megahertz. But one challenge is that this G0 is really small as compared to anything else. But then there are tricks. Turns out that if one pumps the cavity pretty strongly, so that this NP is not only order 1, but for example 10 to the 6, this will enhance the effective coupling from G0 to capital G. This grows with the pump strength, but it also linearizes the coupling. So this capital G now can be very substantial. And there's some pumplet tuning, and cooperativity is an important parameter which characterizes the interaction strength. And by putting there several pumping tones, or in other words, modulating the microwave pumping tones, one can design almost arbitrary Gaussian quantum operations. The limitation is that this interaction is linear, but it's linearly coupled linear oscillators, but on the other hand, they are extremely ideal. And this latter thing is the nice thing, which allows to do a lot. They are linearly coupled linear oscillators, but they are extremely linear. These drumhead oscillators have been used in very successful many experiments. This is some stylized image. In this proposal, we are interested in using a bit different type of oscillators. Same way as you can put transmos to 3D cavities, you can put there also these mechanical oscillators. And this matches well with this kind of design where there's freestanding membrane, can be millimeters in size. Often the natural choice is silicon nitride. That's the very standard material. So it's this one, and then there's some metallization, which will be an antenna. So it will extend here, this blue one to the left, and then on another chip there's also an antenna extending to the right. And these antennas allow to couple these vibrations to the 3D cavity. And in practice, there's 2 chips which are flipped together with very narrow vacuum gap there in between. And there you see these 2 chips. A nice thing about these large membranes is that they can have extremely nice Q values, even up to the 10 to the 9. Right, so that was about cavity optomechanics, mechanical quantum systems. Then a few words about gravity, which is not too strong as we know. So I'm often now here thinking of 2 equal masses of M, capital M, separated by the center of mass distance, capital D. And would be interesting to compare the gravity between the Coulomb force at the same distance between, for example, 2 electrons. So Coulomb force is a few orders of magnitude bigger than the gravity. Then the question arises how you can never ever observe gravity anywhere because this Coulomb force is so much bigger. But then you realize quite soon that the Coulomb forces, they tend to be, first of all, confined inside the atoms, and second, in conducting systems, they become cancelled to the outside world. And so one further thinks, if you have 2 spheres, for example, of radius r, pretty close to one another. So this D is sort of, no, actually no, there's this wrong. This should be D equals roughly R. And then you notice that the gravitational force is proportional to the fourth power, or the size of the object. So it becomes really small rapidly when you make things small. Scales badly. When you try to, would be interested to observe gravity between small masses. But this was done already more than 200 years ago by this Cavendish experiment. This is from the Cavendish paper. It's a bit hard to understand, but they have these 100 kilos lead spheres. These big ones, they are called the source mass, which produce the gravity, and then they have these little spheres, which are about 1 kilo, and they are called test masses. And this is a torsion balance. So, well, depending a bit where these source masses are, there will be slightly different torsion produced by this kind of system. And he was able to measure very accurately the capital G constant. And the forces here, they are a few tenths of nanonewtons between these. So using, given the technology those days, this is quite remarkable. There has been a lot of fundamental research interest trying to measure gravity between very small masses. And one motivation has been test this one. This, in many theories, you will get the correction to the 1 / distance potential by this Yukawa kind of term, which is this one. So that the gravity will be possibly just a guess, modified at very small distance. The lambda is some length scale. Nobody knows what this is. It could be the Compton wavelength. It could be the Planck distance. And this has been measured in very similar systems as the Cavendish experiment. And the world record of lowest mass is a bit around 1 gram. And nobody has found any deviations to this Newton's law. Okay, that was the introduction. Then what is our proposal? Then first of all, to measure gravity between very small masses using these mechanical oscillators. How big is it? If we have 1 milligram of mass, 2 masses, the gravitational force between them at some relatively small distance will be 0.1 femtonewtons. Is this big or small? Answer is that it is huge, because it's 10 orders of magnitude bigger than the what you get from mass sensitivities of some nanomechanical mass sensors. So this is, given this is instantly observable. However, problem is that gravity is produced by other things as well, in addition to these masses. And as a static force, you just cannot distinguish this from anything else. So you have to modulate something. And the obvious thing is to have 2 mechanical oscillators which are coupled through gravity and through nothing else. But then you work out numbers. There will be the essentially this gravitational coupling energy, this delta F0. And depends pretty strongly on the distance, and depends 1 over frequency. If you work out numbers for something like 1 kilohertz oscillators, 1 round of energy swapping would take a couple of 100 years, so no go. Maybe for 0.1 hertz oscillators, who knows? But these kilohertz oscillators, which you might bring to the quantum limit possibly, no go. So you have to do something else and really study this bidirectional interaction. But anyway, the mechanical oscillators, naturally, they are very sensitive force detectors, the most sensitive. And there was this proposal from 2016, which is our motivation, to develop this quantum proposal. And these from the Vienna Aspelmai group, and they proposed a way to measure gravity between a few tens of milligram masses. That was at room temperature and using a very low frequency oscillators. And point is use a resonant enhancement or the weak gravitational actuation. They have this is the source mass, and they have some kind of piston system which they wiggle it back and forth quite a lot, and then they have the test mass attached to some cantilever or some mechanical oscillator. So they modulate the gravity coherently on the resonance frequency of this one. And they conclude that they can see this when the motion amplitude here is on the order millimeter. Okay. So how to first of all translate this into the microwave-optomechanics? In the end, we want to bring it to the quantum regime, and that favors that the masses would be pretty small because then the frequencies are higher, and then you have better chance to go to the quantum. But on the other hand, high mass is favored strongly for more sensitivity. So we have been figuring out some sweet spot there. And looks like the answer is something like the frequency will be a couple of kilohertz and the mass around 1 milligram. And we selected the silicon nitride membrane oscillators, which are really big, several millimeters, and they are very high built-in tensile stress, which allows that even though we plug the little gold sphere there, the frequency will still be pretty high. And the silicon nitride has very small mechanical losses. And moreover, this supply can play to the dilution fridges. And this is our proposal recently in the archive. So I'm talking about that. Cavendish experiment inside the deal fridge. We have indeed two of these, what I mentioned, these oscillator assemblies in the 3D cavity. And they interact, these spheres interact gravitationally. The mass of this membrane itself is really small. So this is the side view. So the membrane is here, that vibrates up and down, and then there's in the center, there's sitting the gold sphere. And then this other chip is the, what I said, the flip chip, other part. So this could be the test mass, and then there's similar, more or less similar is the source mass, and this is actuated, for example, by voltages. And this is then the kind of it needs 4 chips. It's not very complicated structure. It would be very tempting to just press all of these 4 chips together. It would be very simple to make, unfortunately not possible, because there would be huge cross-coupling just mechanically through these chips. So in practice, they have to be physically separated. They have to be in separate 3D cavities like this one, and then these will be pretty close to one another. And this distance here is on the other few hundred microns or so. But this part is definitely doable. Not the simplest thing, but doable. And then we have made quite detailed analysis of these prospects. This is a console simulation of the thin silicon nitride membranes with high stress. It's 5 millimeters in size, and then there's the 0.5 millimeter diameter gold sphere. And this is the mode shape. And you can easily imagine what the drum type of mode would look like if there's no mass loading here. So it's a little bit modified from here. Bad thing is that there's very strong kink in the mode profile there, and that usually leads to increased losses. But we can anyway console that the Q of this one should be about 10 to the 7, 2 kilohertz frequency, and this 10 to the 7 is enough to do everything what I'm saying. And we have to actuate the source mass, which is here, sinusoidally. So these two oscillators, they have about the same resonance frequency. And the actuation is around this omega g is about the omega naught. Amplitude is dxs, and then this test mass oscillator will respond resonantly pretty strongly. It will feel this kind of force, and that is proportional to the size of the spheres to the third power. So this depends strongly on the size of the spheres and rather strongly on the density. So the material has to be as dense as possible, and that's why we use gold. Something about noise. That's the interesting question. Can one see it or not? What are the noise contributions? One is the mechanical Brownian noise. This phonon number, thermally excited at even at 10 millikelvins, about 10 to the 5. So that really turns out that will, in this first case, totally dominate the noise. Other is that there's the amplifier with added noise in added something like maybe 10. Turns out this is totally irrelevant, which makes the experiment easier. And then there's also a quantum Backaction, which in this case is also irrelevant. But what is relevant actually is this one. If you have a pulse tube dilution fridge, it vibrates like mad with this this vibration spectral density, this SXE. E is for external, and it's proportional to the fourth power of the frequency, which seems to favor low frequencies. Unfortunately, also this vibration spectral density grows very dramatically at low frequencies. So it turns out actually that this becomes the bigger problem the lower frequency you have. So what one can see, this is the force amplitude, and this is the actuation frequency around the mechanical frequency. So these are the force amplitude or force sensitivity. So it is the best, lowest on resonance. That's where the oscillator responds the best. And then these blue lines, they are the gravitational signal at different actuation amplitudes. And if the sensitivity is below this line, then you can see it. And we see that, for example, the default is Q is 10 to the 7. We see 1 micron actuation of gravity within a quite nice, reasonable integration time. Right. So we have to wiggle the source mass at 1 micron only to see the gravity. And if we have Q of 10 to the 8, which may not be realistic, then we can go down to, by a longer average, maybe down to 100 nanometers. Then, so we can, looks like this, observing the gravity between extremely small source masses seems to be in reach. I will later tell you a few words about these engineering challenges. But then the interesting thing, can we do quantum gravity? Because we know how to quantum these mechanical oscillators. Answer is that not quite, but we can do first steps towards that direction. So we learned at school that quantum mechanics and general relativity do not like one another. For example, in quantum mechanics, time is very absolute thing, whereas in general relativity, time is a dynamical variable. And one can say that the main question here is that if you create a quantum superposition, is the produced gravitational field a quantum superposition of the two fields? Question is unclear theoretically, not to mention experimentally, because this you have to have spatial resolution of 10 to the minus 35 meters, the Planck length, to test this. We don't have it. And also a pretty nice time resolution or high energies. But one nice thing is actually if you convert this Planck energy to mass, what you get is 20 micrograms, which is more or less what we have. That's a bit mystery, why it is so small, sort of kind of down to earth scale. And but there's plenty of theoretical ideas how to use some kind of indirect measurements to try to do quantum gravity in the lab. And this is used, for example, some quantum mechanical oscillators. There's, for example, proposals that theories that quantum gravity will lead to modification of the commutation relations, which will make some mechanical oscillators nonlinear. And second, this is maybe the most famous proposed first, maybe first by Penrose, that the gravity could be the reason for macroscopic quantum superpositions to stop to exist. And then the gold standard would be create truly spatially separated superposition states of two massive objects, and these interact through gravity. And if they, for example, entangle through gravity, this would be pretty much the evidence of quantum gravity. But this last one in particular, it's totally beyond reach currently, and that I'm not going to do. But something what I'm proposing is sort of not quite on this list, but it is the first step towards this last one. First question to try to answer is that if you have a pure quantum state, how does that respond to gravity? Answer has been known since 1975. And the answer is boring, that you just add the gravity as an extra potential, which will change the phase of the wave function. But this was done for individual neutrons. But then if there's the word massive here, what happens? I don't know. Worth checking. Then the next interesting question, what if you have a mass which is producing observable gravity, and that is in the position of which is in a non-classical state? I'm not here saying that really a spatially separated superposition, like spaced by microns, because that's not possible currently. But anyway, that it is some kind of superposition state. That's already kind of interesting question. Maybe the most interesting is that you have these two gravitating oscillators and you make them non-locally quantum entangled. What happens? I don't have any smoking gun to search for, but I think these are anyway worth making these experiments. Answer is not clear what happens. And there's a couple of possibilities what to do experimentally. One can do ground state cooling. First of the test mass oscillator, this is the easiest. Then ground state cooling of the source mass oscillator. And these ground states, it's a bit matter of taste. If one can argue that they are not quantum, but they are quantum in the sense that the quantum fluctuations are dominant. What happens when you do bring gravity there into play? Nobody knows. And the states I'm talking about, they include the gravitational driving, but they are pure quantum states displaced by the gravity. Then what can realistically kind of do is squeeze the test mass oscillator, squeeze the source mass oscillator. In that case, the gravity is already produced by non-classical objects, and then two more squeezed total system. Then there's engineering how to prepare these mechanical quantum states. I can't go to details, but this is standard. We have done this in these more simple systems. One way is using reservoir engineering, which means that you design some kind of interaction with the cavity that will pull the mechanical system into a stabilized, for example, squeezed state. So this mechanical oscillator is coupled to very hot reservoir, but then you couple it strongly to something cold, or even better than cold, it can be some very nicely structured reservoir which brings this kind of pulls this system into something exciting. In this experiment, challenge is that this requires the cavity line width to be smaller, or at least similar to the mechanical frequency. Number says about a few kilohertz, which means the Q value of the cavity has to be a couple of millions. With the 3D superconducting cavities, some particle accelerators have reached the Qs of 10 to the 10. But when you plug there these large chips which contain all kind of epoxy glue and something, we are still two orders of, no, actually 1 order of magnitude from this one, or 1.5 orders of magnitude. So getting here is in principle possible, but will be challenging. But if we get this 2 kilohertz of cavity line with Q of 3 million, we can do instantly these first experiments. Then we can also create squeezed states. It involves this kind of 2 pumping tones around the cavity. Given this kappa, we can do it instantly. And same for both test and source oscillators. We can create also entangled states in this system, given the kappa I mentioned, same way as we did for normal mechanical oscillators. I can't go to details how these numbers come from. But it might be that it's not possible to hit this good cavity limit, but then at least this bad cavity limit where the cavity line is big, that can be used for other tricks. For example, feedback-based cooling, which becomes actually favorable for these very low frequency oscillators. And numbers again tell that this is instantly in reach. So this is very soon in reach, I would say. But this can be used only for ground state cooling. To create squeezing or something, it requires different interactions which currently are not available. Then third possibility, working the bad cavity limit, which is natural parameter regime, is to use something known as state preparation by measurement, which means that the strong impulsive measurement collapses the wave function. And this has been theoretically shown that one can do everything, all these possibilities which I mentioned, using these operations with realistic numbers. So this looks the most promising currently. Maybe I skipped that. Maybe a few words. Turns out that now the detection of the gravity becomes more difficult actually in the quantum limit. One needs very good amplifiers. One has to worry about the quantum backaction of the measurement and so on. But it's still possible. Some words about engineering. Big thing will be vibration isolation in the Dilfrits. One needs, for example, 120 dB of isolation between the pulse tube fritz and the test mass, but we have designed this kind of suspension assembly with few kilo masses and so this kind of ring springs which will do the job. And maybe I skip that. Then some preliminary first experimental tests, just checking this kind of mass loaded silicon nitride oscillator. So we have a few millimeter silicon nitride membranes. It's this circle here. And this is the gold sphere glued there. And then there's these mirror-like side walls which are tilted. They reflect the image of the gold sphere. So these 4 here, they are mirror images of the gold sphere. And then we stuff this into the 3D cavity. And it worked. We can identify 3 mechanical modes due to this system. This is the main drum mode, and then there's these two lower frequency modes where this sphere is sort of wobbling back and forth. And this main mode had a very nice Q value, nearly 1 million. So this is the zoom into the spectral density at about 2 kilohertz. Looks like this. And we are so at this Q value of 1 million, if we can just be able to put these two boxes close to one another, we can see the gravity almost right away. So this looks very promising. I was afraid that these very dirty fabrication like glue or putting there some gold particles will totally ruin the cube, but that was not the case. In summary, observing the gravity produced by this 1 milligram mass is possible. Why to do it? Well, interesting. That is one then requirement to do this. Push this to the quantum regime. We can make the source mass to be in a non-classical state. It's pretty likely it's possible. Observe the gravity, and then it's a bit on the edge, but if one can create this entanglement and the self-gravity in the system, that is plausible, I would say. And then this is the archive reference where there's plenty of details. So thanks for the attention. I'm done. Questions?
Okay, thanks a lot. Questions, yes.
Hey Mika, thanks for the very interesting talk. You did give kind of good reasons and good nice experiments, like where you could observe the effect of gravity for quantum states as well. In some of the case, you said that the result is boring. It's just by like adding a potential term to the Hamiltonian. And I guess my question here is that is in the experiments that you are now describing here, do you expect to see something else than just the effect of basically that, okay, these two masses are interacting with 1/r² potential term? Are you expecting to see something else? And if yes, what would that possibly be?
That's a very good question. I don't have a theory what that could be, but I hope to see something.
Well, that would be great, of course. Yes, yeah. But I guess if quite often in experiments we see a lot of things, and first we might think that, oh, this is because of gravity, but maybe it's because of some technical issue. So sure. I guess how would you differentiate between a technical issue and the actual gravitational effect?
Well, there's first of all to observe that there's some kind of 1/r² or 1/r potential, and that is a gravity. That actually I believe is rather simple, and there's very many things. One is this experiment, it requires actually tuning the distance between the boxes or masses inside the fridge anyway, because one needs to put them close to one another, and this allows also observing this based on the distance dependence. One can pretty well separate gravity. But then to observe that if there's something else in addition to that I don't know, because unfortunately I don't know what there could be, but somebody has ideas, let me know.
Okay, but it's very exciting. Thank you, Mika.
I think Fabian has a question.
Yes, thanks for the nice talk, Mika. I'm a theoretician, so I'm thinking about other things. So, I mean, what is also interesting about gravity is, of course, gravitational wave. And I'm not sure whether it's easier or less easy than to see quantum gravity. Do you think about that? So maybe you have to put the masses further away from each other or something.
I have thought about that, and actually in these particular systems, I don't know how that would happen, but in principle it would be possible that you just have two membranes very close to one another. And when the gravitational wave comes, it will sort of jiggle the distance between these membranes, and that would cause one of them to oscillate, or both. But the numbers there are not very great. You know, if you have 100 nanometer distance versus kilometer distance in the LIGO will win over in sensitivity.
When you finished, I have a question, Mika.
Yeah, please do.
You did say, refer to quantum mechanical time as absolute quantity. Do you mean that in a very absolute sense, or anything more than just a time parameter in, for instance, Schrödinger equation and so on? Because one way of looking upon time is simply counting events, basically at the events happening that is really marking the time, and you sort of clock them with clocks, etc. But time is not a quantity in itself. So what do you say about that?
What to say? What I think it's indeed just a parameter.
Right. Okay.
But in relativity, as we know, it's not quite so.
Yeah, yeah.
Depends on observer.
Yeah, yeah. Space time, all that. Sure. Yeah. Okay. Thank you.
Okay, I don't see anybody raising the hand or taking the floor. So thanks a lot, Mika. This was very exciting proposal and things to do.
Thanks.
And okay, let's move to the next talk. Fabian Hassler is online.
Yeah, I try to share. Can you see what happens?
Yeah, it works.
It works. Perfect. Yeah. Okay, so welcome to my talk. I think you see my mouse. And I want to tell the story about photon counting below a bifurcation threshold. We actually put out this work last week, and actually work has been done by Lisa Arndt. I'm just here to report on it. If you want to know more information, so here's the archive reference. Okay. So first, what is bifurcation? So, I mean, I do a simple introduction. So you have a gray beam, and you put some mass on top and nothing happens. And then you put a bit more mass on top and nothing happens. And you put a bit more mass on top and suddenly the beam buckles. And there's a certain point where this happens. And that's a bifurcation threshold where you go from one stable position to two new stable positions. So either towards the right or towards the left. But of course we want to do quantum mechanics. So fluctuations actually makes the threshold not so sharp, but there's actually, you know, already before you actually hit the threshold, there's something happening. So just to, I mean, this is a very, you know, simple picture, and it's kind of too simple. Of course, what I'm studying is quantum fluctuations. So then one should actually put this system at finite frequency. So think about this in a rotating frame. So that's much more better. So you have like an oscillator, and then this physics actually happens in the slow variable in the rotating frame. And then quantum mechanics, we look at low temperature. Quantum mechanics actually leads to the fact that the system already experiences this bifurcation threshold before you actually hit this classical value of bifurcation. And we're interested at what kind of photons, this quantum of excitations are produced below the threshold. So that's also, you know, the talks. I want to convince you that kind of the photon counting statistics is in a way universal below the bifurcation threshold. And then I will explain what kind of statistics you can expect, and also point out a microwave setup in which you can observe this physics. Okay, so the system which we want to investigate are driven dissipative systems. So there's also a drive. We always are at a certain frequency. So we look at the physics in a rotating frame at this frequency. And we have always photons which actually go out. But we assume that the photon loss is kind of low compared to the frequency. And then we can write down, effective degrees of freedom, the slow dynamics in the rotating frame. And we would like to write down some equations for that. First, we try to look at the classical equations, which we expect. And so the physics close to this bifurcation threshold has been classified. And you can actually write down a certain set of equations. And depending on which class you are, there are different set of equations you want to write down. For us, because at some point we actually want to do quantum mechanics, it's actually important that we have a path integral description of this, and that actually you can do. And there's actually something which is called Martin-Sicher-Rose action, which is an action which I just write down in a second. So, for example, just to give you some concrete ideas. So, for example, if your degrees of freedom which you're interested is x, then you write down a differential equation x dot. There's certain damping, and then there's a force that is applied, which is the drive which you put in. And then, of course, it's also important that we have noise. And then in the classical setting, the noise is given purely by temperature. So you expect that the noise source is proportional to temperature, and the dissipation constant, which is the fluctuation dissipation theorem. So then this Langevin equation is actually equivalent to a path integral description of the whole thing. So that's what actually has been pointed out by Martin, Sicher-Rose. You actually see that, so this last term here, that's actually the noise term. So if you put that to 0 for a moment, then you actually see you have one variable, which is the x tilde. And the x tilde variable is in a sense an artificial variable. If you integrate over x tilde, you get the delta function with respect to that. So that's just this equation without the noise. And so the last term is actually what leads to the noise. What is interesting is that, so the x tilde is actually a response field. And if you think about this quantum mechanically, you actually have a commutation relation between x and x tilde. And they're essentially canonical conjugate variables. But note that this is purely classical, and this comes just from the noise, because this noise has kind of a similar structure that leads to the fact that you have this equation here. So now we want to actually make quantum mechanics, yeah? So we're not interested in this, easy. So we have a certain bifurcation transition. So there's this action, which would be the classical action to it, but we're not interested at classical noise. So we actually want to put here quantum noise, and we actually want to count the photons that come out. And so for that, it's important that we have a scale, alpha, and alpha you should think about h bar, yeah? So alpha is h bar, and so x squared is kind of the quadrature. And if we divide x squared by alpha, we get the number of photons. So that's how we introduce the number of photons. And then we want a conjugate variable to x, which has a commutative relation with is I times h bar or alpha in this sense. And we very naturally get it by dividing the x tilde, which was the response field, with alpha. So then we naturally have the canonical conjugate variable in this setting. And the classical noise, which you had before, we replace with quantum noise. That's just beta, which was before, the strength, which was proportional to temperature. We replace also with h bar, which is alpha. And then we actually claim that this is the action that describes the system that actually suffers from quantum mechanical noise. Is driven by quantum mechanical noise below the bifurcation transition. And you can actually get this action if you start with a Keldysh action for the quantum mechanical system and then expand in the so-called quasi-classical limit. But I just wanted to motivate it from a different perspective. And then, so far it's kind of trivial, but now we actually want to count something. And what we count, and this is actually where quantum mechanics is, it's the only place where quantum mechanics is very essential, is that what you count is actually the normal ordered variable. So you don't want to count x as a classical variable, but you want to count the normal ordered variable. And if you go through the calculation, you actually figure out that this is not written as x in the path integral description, but there's a certain part of the canonical conjugate variable which comes here. So I don't have a good way to actually motivate that, but that's what comes out. And you see also the I here, because I mean the I has to be here because you know, in the vacuum, if you don't drive, there should be actually 0 counting here, so the X actually cancels with the I if you expand out. So chi is a counting field. If you take derivative with respect to counting field, then you get the average photon number and so on and so forth, and you can get actually the full distribution of photons by just calculating the path integral here with respect to X and P, and then taking the derivative. So our claim essentially is, I mean, given this Martin-Sicher-Rose action, there's kind of a canonical way by which you actually write down an action, which is a quantum mechanical action, and by which you can get the statistics of the photons that come out of the system. So now we want to specify what kind of F we are interested and want to investigate. Good. So what we want to investigate is kind of the simplest system, which shows bifurcation. And the application, you know, so a laser transition would be something like that, and also a parametric oscillator. And there are many implementations of this system, but let's not discuss the concrete implementation, but we try to say what is kind of the force we want to have. And we have a cubic term, and then there's a linear term, and these are essentially our parameters. And in this space of A and B, which are these parameters, if you plot the potential, so not the force, so the potential, we have 1 minimum down here. Up here, we get 2 minima. So if you go across here, we go from 1 minima to 2 minima. And on the side here and here, we have 1 minima, which is lower, and it's kind of a second dip, which is developing. So for example, if you go through this center of the cusp, then you get this pitchfork bifurcation, which I showed already in the buckling. So down here, you have a single minima. Once you hit this point, you get this bifurcation. And up here, you get 2 minima, which are these two separated by an unstable point, which is the point here in the middle. But you could also go through this system kind of somewhere on the side here. And then you get a fold bifurcation. So fold bifurcation is kind of, you know, you have 1 minima here, which stays and remains to be a minima, but at some point there's a second minima appearing somewhere here, which is separated. So if you think about the equilibrium statistical mechanics, this is kind of like a first order phase transition, whereas this is a second order phase transition. So this depends on whether you go here right through the cusp or here on the side through the transition. So now we plug in this F and try to figure out what is the kind of statistics which we get out, and is there anything universal about this if you go very close to this threshold. So just to reiterate, so this was our action which I wrote down, and it's essentially like a Hamiltonian system. So this is like the Hamiltonian, and it's kind of imaginary, which is due to the fact that the whole system is dissipative. Okay, now, I mean, at some point we have to solve something, and we actually have troubles with this whole integral, because in general, these path integrals are not solvable unless it's kind of a Gaussian path integral. So what we do is kind of very brute force, and at first you think you'll get nothing interesting out. So we say you should stay away from this blue area. So this blue area, which is very close to this bifurcation threshold, fluctuations are huge. So in here, you're kind of dominated by fluctuations. And kind of out here is like where you would expect that mean field holds, like in a usual phase transition. So out here, you can actually expand the action in second order. And now you might say, if you expand the action in second order, all what you get out is Gaussian, but that's not true. So the interesting thing is, even though we expand the action to second order away from the bifurcation point, the statistics is still not Gaussian. So this is different from equilibrium physics, where kind of the only interesting fact is kind of in this blue regime, where people have figured out like renormalization and stuff like that. I mean, this is also something which one could do, but we're kind of doing the first step, which is the stuff out here. So we expand H around the saddle points, and then we look at the long time limit, where all the cumulants actually become linear in time. So the saddle point structure is the following. So at the pitchfork bifurcation, we only have one saddle point, which essentially is at 0. And across the bifurcation transition, this saddle point becomes unstable. So that's essentially the transition. We go from a stable to an unstable point. More interesting is the fold bifurcation, where we also have the saddle point here at 0, which is just the only stable minimum down here. And it actually remains stable, even going across this line, because we know that the minimum still remains. But somewhere at some other point, there's a second minima appearing. But this minima is not yet a saddle point if you're below the threshold. And it turns out that there's kind of something like a virtual saddle point appearing. And physically, it's the following. So what we have down here, we are at this minima of the potential, at one minima of the potential, but then we do quantum tunneling in the second minima. And these tunneling processes are actually suppressed with a suppression, which is just a tunneling barrier to go from one to the other side. But this suppression actually, so delta tells you how far away from the threshold we are. So the kind of the exponential suppression of the second saddle point becomes less and less the closer you get to the threshold. And in fact, what we actually find is that in both cases, there are cumulants diverging if we hit this bifurcation threshold. But for the fault bifurcation, it's actually the second saddle point, which is the one which we reach by quantum tunneling, which is the relevant one, whereas the other one just remains stable all the time. So now I just show you the results. I mean, we do the path integral. That's a certain technical thing to be done. And then we kind of figure out how the critical exponents of the different cumulants behave with respect to how close we get to the threshold. Note that it's very similar to equilibrium physics, but in equilibrium physics, we only care about the first moment usually. We want to know how the magnetization diverges if you kind of approach a phase transition, or maybe sometimes the second moment, but the higher moments don't appear because everything is Gaussian. Whereas here, all cumulants follow a certain universal behavior, and all of them have critical exponents. And the critical exponent for the pitchfork bifurcation, so going in here, are different from the ones in the fold bifurcation. In particular, you can already observe the difference by observing the Fano factor. So the Fano factor essentially tells you how many photons are correlated with each other. And the number of photons that are correlated grows in both cases, but here it grows quadratically, whereas here it only grows linearly. So there's kind of much more fluctuation happening in this pitchfork bifurcation than if you do the experiment for the fold bifurcation. Interestingly, the divergent timescale, so I mean, these bifurcations are connected to the fact that there's a timescale which becomes very long. You can also think about the other thing. There's one degree of freedom which actually kind of starts. This is the one which buckles in the buckling transition, which starts accumulating a lot of photons. And in both of these cases, this actually diverges like 1 over delta, and this is connected to some critical exponents which people have been discussing before. So these are dynamical critical exponents. What is interesting is if you try to see what is the probability that actually detect certain photon current, and you compare it to the naive Gaussian approximation. So in the most naive case, you would just go there and calculate the first and the second cumulant and be done with it. Then you would get the Gaussian approximation, which is this dashed line. But what we show is that actually the photons which appear close to this bifurcation transition are actually not Gaussian distributed, but you get kind of skewed distributions towards a lot of photons. So the photons tend to appear in big bunches of big numbers. What is also interesting to see is that there's a big difference between the pitchfork and the fold bifurcation. So if you look at very small currents, so almost close to 0, then the probability to see such small amounts of currents goes to 0 in the pitchfork case, but it reaches a constant for the fold. And you see it here. So for large deviations, there's actually much more. So for the pitchfork case, there's much more likely to have big deviations towards the positive side compared to the fold deviation. This is actually the same what I told you before, that in the pitchfork case, the Fano factor grows much stronger than in the fold bifurcation. That means that there are much more photons correlated in this case. So now for the implementation. So we actually discussed an implementation which is based on earlier implementations and even experiment which has been done, which allows to test the full Cusp theory. So both the fold and the pitch bifurcation in a single experiment. So what you have is you have kind of a driven chosen junction, so it's driven by a voltage, and there's a resonator close by, which is actually the one which where the photons accumulate, and then you actually leak them out and detect them somewhere later in the detector. So alpha, which used to be the H bar, kind of like playing the role of H bar, which tells you kind of how quantum the whole system is the characteristic impedance with respect to quantum impedance. And then what we also want to do, we want also have an additional coherent current drive. So without this drive, it's just a setup of a parametric resonance if you make sure that the voltage is actually related to, is at such that you get double the excitations due to voltage in the resonator. So the ohmic of the resonator, 2 times the ohmic of the resonator corresponds to the voltage. But then you additionally apply a coherent drive, which is the second axis for this Cusp catastrophe. And so that actually excites signal excitation. So that's actually on resonance with the oscillator. So then experimentally, you have both of these A and B parameters. So you can change the Josephson critical current and as well as the external drive and kind of map out the full Cusp catastrophe. So our prediction is that you can actually get a different divergence of the Fano factor if you go here through the Cusp with respect to the when you go here some on the side. Yeah? So the conclusion is the following. So what we claim is that there's a generic characteristic function of the photon counting based on the universality of Martin-Sicher-Rose action. So if you have a certain system and there's a bifurcation happening, then given kind of the class in which the dynamics is, there's a Martin-Sicher-Rose action to that. And given the Martin-Sicher-Rose action, there's kind of a generic way to write down a quantum action which accounts for the counting of the photons that come out of this system. Then we showed that the photons that come out of the system actually diverge, kind of approaching this, for example, the critical values in the Cusp catastrophe. And the divergence is universal. So the critical exponents don't depend on the concrete system by which you implement it, but only like in which type you are. So for example, whether you go here through the pitchfork bifurcation or somewhere on the side through the fold transition. And then this microwave setup allows you to actually measure these critical exponents. For example, we predicted that the Fano factor diverges like 1 over this parameter distance square here if you go through the Cusp, and only like 1 over the distance somewhere on the side. Of course, there's kind of a crossover behavior if you kind of go directly here compared to here, and we can also kind of tell you at which point you would expect the pure fold critical exponent compared to the pitchfork critical exponents. So that's actually all of it. For more information, you can either ask me now or you can find more information on this archive paper which we put out.
Okay, we better ask.
I was much too fast, right?
No, you are in time, everything is fine. So, is there anybody who'd like to ask a question? I want to ask because this microwave setup is somehow relatively well. I mean, other people have studied similar things. So the components, at least, of what you have here seem to be available, and parts of these experiments, I think, have been attempted, but I don't see the. Can you clarify the connection maybe with?
Yes, I can explain what I'm hidden below the rack and what makes this experiment difficult. So typically people do these experiments and they're kind of in the gray regime. Yeah? Mm-hmm. Or they kind of have a classical state of light in the resonator. So in the gray regime, you actually have you have a coherent state essentially in this oscillator, and then you kind of measure the statistics. So what we try to understand is like how you come from no photons down here to kind of this coherent state. So we're interested in kind of what happens close to the transition. And the problem there is, of course, that there's only very few photons, because all the photons that they actually have in the resonator then are due to quantum fluctuations. Mm-hmm. So our theory, and there's this alpha parameter, which is kind of, this impedance of this resonator. So our theory works if this alpha parameter is small, but once this parameter is small, there's of course only very few photons. So in the experiment, you actually want the alpha or the C naught to be rather large, such that you have a lot of quantum fluctuations. So you should actually build an oscillator where this characteristic impedance is close to the quantum impedance, but kind of below, maybe a factor 10 below or something like that. Such that you actually already get a signal before you actually should get a signal if you just think about it in purely classical terms. You understand what? Yeah. So somehow the theory is about quantum fluctuations, and the typical experiments are about the classical states. I mean, I say coherent state, they also see deviations of kind of classical states, but these are kind of small deviations on top of usual coherent states, or squeeze states or something like that. I mean, in some sense, squeeze states are also classical states in this setting.
Mm-hmm. Thanks. Yes. Okay. Any other questions? I don't see anybody raising a hand or taking the stage. So then I would like to thank Fabian and to thank everybody for this session today and for the previous session also today. And see you tomorrow then. It was a very good and interesting discussion that we had and very nice talks. Let's meet tomorrow. Thanks a lot.
See you tomorrow. Bye-bye.
Thanks. Bye.